Hello. So, in the previous modules, we have looked at the comb type pilot or CTP for OFDM channel estimation. Let us now look at an example for the same thing, that is comb type pilot based OFDM channel estimation. Alright, so what we want to do starting today's module is look at an example for our comb type pilot, that is CTP, comb type pilot or CTP based OFDM channel estimation. Alright. So, let the symbols loaded onto the subcarriers. Alright. So, we will consider again, we will start by considering an n equal to 4 subcarrier system. Okay. And in this, the information symbols, alright, let the symbols loaded onto the subcarriers, we are going to set them as capital X0 equals 1 plus j, capital X1 equals 1 minus j, capital X2 equals 1 plus 2j, capital X3 equals 2 minus j, that is the same as before. So, these are the n equal to 4 symbols loaded onto the subcarriers, and these n equal to 4 symbols are loaded, basically that is the nomenclature that we use, that is these are loaded onto the n equal to 4 symbols are loaded onto the subcarriers. However, as we said in comb type pilot based channel estimation, not all the subcarriers are loaded with the pilot symbols, only a few of the subcarriers are loaded with pilot symbols. So, let us say again that X1, again as in what we have done previously, that X1 and X3 are the pilot symbols, that is L equal to 1 to 3 are basically your pilot subcarriers, and X1 and therefore X1, X3 are basically the pilot symbols loaded on the pilot subcarriers, and again X0 and X2, these, that is corresponding to L equal to 0 comma 2, that is these L equal to 0 comma 2, these are my data subcarriers, alright, X0 comma X2 are the data symbols, alright, X0, X2 are basically the corresponding data symbols loaded onto the data subcarriers. Okay. So, now what we do is we have this comb type pilot arrangement, that is corresponding to the 4 symbols X0, X1, X2, X3. Now, what we are going to do is similar to what we have done before, these are the symbols loaded onto the subcarriers. So, we are going to take the n equal to 4 point IFFT, inverse fast Fourier transform, to which basically generate the time domain samples, the small x0, small x1, small x2, small x3. Okay. So, now we consider the n equal to 4 point IFFT to generate the time domain samples small x 0, small x 1, small x 2, small x 3. These are basically, you remember, these are the time domain samples. And these are generated as xk equals, as we said, these are the endpoint IFFT summation L equal to 0 to 1 e power j 2 pi k L by n, and we have already calculated this before previously in the context of the OFDM symbol. We have calculated the time domain samples already. So, I am going to simply write that down over, write those down over here. So, the time domain samples are given as x 0 equals 5 by 4 plus 1 by 4 j, x 1 equals minus half j, x 2 equals minus 1 by 4 plus 5 by 4 j, and x 3 equal to 0. So, the block of time domain samples therefore is given as given as 5 by 4 plus 1 by 4 j minus half j zero, and now you take this 0, place it over here. Remember, this is basically adding the cyclic prefix, and this is the block that is transmitted. This is the cyclic prefix added block. So, this is basically your block with cyclic prefix added, and this is transmitted over the ISI, or basically the inter-symbol interference channel. So, you are taking the time domain samples of this comb type of this subcarriers on which the information symbols and the pilot symbols are arranged in a comb type fashion. All right, you take the endpoint IFFT to generate the time domain samples, add the cyclic prefix. Now, the cyclic prefix added block is what is actually transmitted over the ISI channel. All right, and similarly, similar to several times before, we are considering the 2 tap ISI channel, that is yk equals h0 xk plus h1 xk minus 1. Basically, what is this? This is your L equal to 2 tap ISI channel. This is the L equal to 2 tap ISI channel. Okay. And therefore, the action of the channel tap is now y is equal to the action of the channel, because you are transmitting the cyclic prefix added block of samples. Action of the channel is basically circular convolution in the presence of additive noise. All right. And therefore, now once you take the FFT of the output samples, FFT of the received output samples, FFT of the received output samples, I have YL equals HL XL plus VL, where YL is the output on the Lth subcarrier, this is the output on Lth subcarrier, this is the channel coefficient on the Lth subcarrier, this is the symbol transmitted or symbol loaded, and this is the output noise on the Lth subcarrier. All right. So, this is the model that is we have, that is the capital YL equals capital HL times the capital XL plus V, capital VL. This is the symbol that we have. This is the system model that we have in the frequency domain, that is the input output model across each subcarrier, that is across the Lth subcarrier. All right. And now we said in the comb type pilot, in the comb type pilot based channel estimation scheme, we have to extract the output symbols corresponding to the pilot subcarriers. All right. So, that is what we are going to do next. So, let us now, let us say the output samples, let us first consider the output samples. Let the output samples be y0 equals 1, y1 equals half, y2 equals half, y3 equals 1. Therefore, the output symbols YL implies the output symbols YL are basically, remember, the capital YL are given by the FFT of the time domain sample small yl. So, they are basically, you have k equal to 0 to n minus 1 yk, that is FFT e power minus j 2 pi kl divided by n. Therefore, these YL, these are basically given as FFT of time domain FFT of the time domain output samples yk, and that is what we have written over here. And we already said y0 equal to y1, y0 equals 1, y1 equals half, y2 equals half, y3 equals 1. So, now once we take the FFT, and this is again something that we have calculated before, that is, this is again considering these output samples, we have calculated the FFT of these output samples in the context of the OFDM, for the OFDM example, and therefore, these the output symbols across the various subcarriers capital Y0 are given as 3, that is, once you compute the FFT, these are the values that you will get. Y1 equals half plus half j, Y3, Y2 equals 0, and y3 equals half minus half j. Now, extract the symbols corresponding to the pilot subcarriers. Now, we extract the symbols corresponding now we expand the symbols corresponding to the pilot subcarriers, that is, pilot subcarriers are L equal to 1, 3. Therefore, we extract the symbols corresponding to the pilot subcarriers. Therefore, it goes without saying these are capital Y1, comma capital Y3. Alright, since the pilot symbols are transmitted on subcarriers 1 and 3, that is L equal to 1 and 3, the symbols corresponding to these subcarriers are capital Y1 and capital Y3. And now we extract them, that is we use these and these only for the purpose of channel estimation, because these are the pilot symbols or these are the pilot subcarriers. Okay. So let us do that, and what we have is, now if we write this model, remember that is what we have seen, if we write this model across the pilot subcarriers, I have Y1 equals X1 H1 plus V1, and we also have Y3 equals X3 H3 plus V3. Now writing this in matrix notation, what I have is Y1 Y3 equals X1 X3, the diagonal matrix times this vector H1 H3 of channel coefficients plus V1 V3, and remember this we call Y check, this we call X check, this we call the vector H check, this we call the vector V check. And now the least square score, therefore we have the system model, which is basically your Y check equals X check plus V check. This is the output vector, this is your pilot matrix, this is your channel vector containing coefficients capital H1 capital H3, this is your noise vector. Therefore, the least squares function, now at this point again this is something you should be familiar with, least squares function for channel estimation, that is your Y check, that is your Y check minus X check H check whole square, that is minimize the least squares cost function Y check equals X check minimize norm of Y check minus X check H check whole square, and the least square solution, therefore the channel estimate H hat, remember, is basically your X check Hermitian X check inverse X check Hermitian Y check. This is the least square solution, and remember we said X is this X check matrix is a square matrix, it is invertible and it is diagonal, and it is invertible, basically it is an invertible matrix. Therefore, this can be simplified as, since X check is invertible, this is basically equal to your X check inverse times Y check, and since X check inverse is diagonal, the inverse of X check is simply the inverse of the diagonal elements, that is 1 over X1, 1 over X3 times Y1, Y3, and this is basically your estimate. This is your estimate of the channel coefficients. Therefore, now I can calculate the estimate H hat 1 as simply that is your y1 divided by x1, and we know both of this. For instance, y1 is something that we know from here, this is your value of y1, and x1 is something that you know from here, that is a symbol loaded, that is a pilot symbol loaded onto subcarrier 1, that is 1 minus j, and therefore, what we have is now I can compute h hat 1, all right, the h hat 1, capital H hat 1, which is the which is basically, remember, capital H hat 1 is estimate of the channel coefficient across subcarrier 1. What is this? This is estimate of channel coefficient across subcarrier 1, and this is equal to, basically this is equal to your what is this? This is basically your half plus half j divided by 1 minus j, which is basically equal to, again just rewriting it using the properties of complex numbers, that is 1 plus j divided by, well, 2, which is equal to 1 over 4 times 1 plus j times 1 plus j, which is 1 plus j square, and you can check, this is basically, this is equal to half j, all right. So, h hat 1, that is the estimate of the channel coefficient. So, what we have calculated so far is the estimate of the channel coefficient h hat 1 across subcarrier 1. This is y1, capital Y1 divided by capital X1, this is half j. Similarly, we can calculate the estimate capital H hat 3 across subcarrier 3, and this is equal to estimate of channel coefficient across subcarrier 3, that is estimate and this is equal to y3 divided by x3, and once again from above we know both y3, capital Y3 and capital X3, that is y3 equals half minus half j divided by capital X3, that is 2 minus that is basically equal to 2 minus j, which is half into 1 minus j into again 2 plus j divided by 5, and you can also verify this. This is basically your 1 by 10 times 2 minus 2j plus j plus 1, and this is equal to 3 by 10 minus 1 by 10 j. Okay. So, capital H hat 3 equals 3 by 10 minus 1 by 10 j. So, therefore, now what we have found is we have found capital H hat 1, capital H hat 3, which are the estimates of the channel coefficients on the pilot subcarriers, that is L equal to 1 and 3. Therefore, capital H hat 1 comma capital H hat 3, which are estimates of coefficients on pilot subcarriers L equal to 1 comma 3 have been found. Okay. And now, what is the next step? Remember, we looked at comb type pilot estimation. From the estimates of the channel coefficients on the pilot subcarriers, we compute the time domain estimates of the channel taps. Remember, that is the next step, and that can be illustrated as follows. So, remember, we have H3 H1, remember, equals H0 minus j H1, and H3 equals H0 plus j H1, which implies, writing this as vectors, writing this using matrix notation, I have H1 H3 equals 1 minus j 1 plus j times H0 H1. So, what are these? Now, these are basically your time domain channel taps, right. These are the time domain channel taps of the ISI channel. These are the time domain channel taps of the ISI channel, and these are of course the coefficients on the pilot subcarriers. These are the coefficients on the pilot subcarriers. Now, therefore, I can find the channel taps as the channel taps can be found simply as H0 H1 equals this 1 minus j, this matrix inverse times H1 H3, and that is basically what we have. And the last step is basically to realize that we have the estimates of these channel coefficients on the pilot subcarrier. So, if we use the estimates here on the left hand side also, you will get estimates. So, these are what are these? These are the estimates of the channel taps. Estimates of time domain channel taps, or basically your ISI channel tap. So, what we have is basically we can express small h0, small h1, the time domain channel taps in terms of capital H1, capital H3. But if you only have the estimates, that is capital H hat 1, capital H hat 3, what you are going to get are naturally basically the estimates of the time domain channel taps, that is small h0 and small h1, alright, and that is how we calculate the estimates of the time domain channel taps. Okay. And therefore, now I am going to calculate this, I am going to substitute capital H hat 1, capital H hat 3. So, this is 1 minus j 1 plus j inverse of capital H hat 1. Now, capital H hat 1 we already calculated, that is half j, this capital H hat 3 we have calculated, that is 3 by 10 minus 1 by 10 j, and therefore, this is equal to, now we will calculate the inverse of this matrix. This inverse of this matrix 1 minus j 1 j, that is simple to compute because it is 2 cross 2 matrix, that is 1 over 2 j times swap the diagonal elements negative of the off diagonal elements. So, this is the inverse of the matrix, this times half j 3 by 10 minus 1 by 10 j. These are the estimates of the time domain channel taps H hat 0, H hat 1, and now multiplying I can find this as basically 1 over 2 j over 2 j (3 by 20 plus 1 by j) minus 3 by 10 minus 3 by 20 j, and now finally you can compute these estimates of the time domain channel taps as basically oops, I think this is not completely correct. I think let me just rewrite this. This is 1 over 2 j minus 2 over 5 plus 3 over 10 j minus 3 over 5 j plus 3 over 10. Okay. And therefore, what I am going to have here is basically what I have over here is the estimates of the channel coefficients or estimates of the channel taps in the time domain, which is basically 3 over 20 plus 1 over 5 j minus 3 over 10 minus 3 over 20 j, and these are the estimates. So, basically what we have is these are the estimates of the channel taps in the time domain. These are the estimates of the channel taps these are the. So, basically these are your estimates of the channel taps in the time domain. Okay. So, what we have computed are the estimates of small h hat 0 and small h hat 1, and these are given as basically small h hat 0 equals now naturally 3 by 20 plus 1 by 5 j, and small h hat 1 equals minus 3 by 10 minus 3 by 20 j. Okay. So, now we have the estimates of the channel taps in the time domain. Now, we have to compute, remember, the estimates of the rest of the channel coefficients in the frequency domain, remember, corresponding to the information subcarriers, that is L equal to 1 and 2, and these can be computed as follows. Now, we have the estimates of the channel taps in the time domain. All that is left is to compute, we have to now compute. So, we have to now compute estimates of, we have to compute the estimates of the channel coefficients H0, H2 for the information subcarriers. And therefore, these can now be determined as, now we have seen that basically, well, H0 equals simply H0 plus H1, that is what we have seen yesterday, that is H0 is the 0th point FFT of the 0 padded time domain channel taps H0 H1. So, this is implies H hat 0 equals small h hat 0 plus small h hat 1, which is equal to 3 by 20 plus 1 by 5 j plus minus 3 by 10 minus 3 by 20 j equals minus 3 by 20 plus 1 by 20 j, and similarly h hat 2, capital H hat 2 corresponding to subcarrier L equal to 2, this can be calculated as h hat 0 minus h hat 1, and this follows, remember, because h of 2 equals small h 0 minus small h 1, small h 0 minus small h 1. Therefore, that implies capital H hat 2 equals small h hat 0 minus small h hat 1, implies capital H hat 2 equals 3 by 20 plus 1 by 5 j minus 3 by 20 minus 3 by 10, I am sorry, minus 3 by 10 minus 3 by 20 j equals 9 by 20 plus 7 by 20 j, that is equal to your h hat 2. So, now basically we have calculated the value of h hat 1, this is the value of your h hat 1, and this is the value of h hat 2. Let us write this down again. So, basically your h hat 1 equals minus 3 by 20 plus 1 by 20 j, and h hat 3, I am sorry, this is h hat 0 rather, this is not h hat 1, this is h hat 0. So, now we have calculated the values of h hat 0. So, I have h hat 0 equals minus 3 by 20 plus 1 by 20 j, and h hat 2 equals 9 by 20 plus 7 by 20 j, and these are the estimates of the channel coefficients corresponding to the estimates of the channel coefficients corresponding to the data subcarriers or the information subcarriers or the non-pilot information or basically the non-pilot subcarrier. So, basically what we have seen is we have seen an example of this comb type pilot based channel estimation scheme, where information symbols, where pilot symbols are loaded only on much fewer number of subcarriers. So, we have seen an n equal to 4 subcarrier example, where pilot symbols are loaded onto 2 subcarriers, that is L equal to 1 and L equal to 3, and the data symbols are loaded onto the remaining subcarriers, that is L equal to 0 and L equal to 2. And therefore, what you do now at the receiver is basically first estimate the channel coefficients in the frequency domain on the pilot subcarriers. These are the capital H1, capital H3. From these, estimate the time domain channel taps in the time domain, that is the small h0, small h1, and from these estimates of the time domain channel taps, re-estimate or recompute basically the estimates of the channel coefficients on the rest of the subcarriers, that is the non-pilot subcarriers or basically the data or the information subcarriers, that is these are capital H0 and the capital H hat 0 and capital H hat 2. Alright. So, this basically sort of comprehensively illustrates a simple example, but comprehensively illustrates the principle behind the comb type pilot based channel estimation for OFDM. And as we have seen, this is preferable compared to conventional channel estimation, where the pilot symbols are loaded on all the subcarriers. In a comb type pilot, remember the pilot symbols are sort of meshed with the data symbols, therefore, you are transmitting only a few pilot symbols, therefore, this is highly efficient because you are transmitting pilot as well as information. So, this improves the data rate of the system. So, that in a sort of a nutshell basically summarizes the intent, the motivation and the procedure for this comb type pilot based OFDM channel estimation scheme. So, we will stop this module here and look at other aspects in subsequent modules. Thank you very much.